Welcome back, Honors Precalc. Pardon my voice. Everybody is getting sick in the Declarico family, and I am no exception. But here we are, we're going to do this. So, we were talking about complex numbers last week, and we need to remember whenever we evaluate with complex numbers, we need to represent negatives under radicals using I so that we don't make a silly mistake that we talked about last week. So, if we were to look at number 1 on this slide, 4i squared minus 2i cubed, the first thing we should consider is, well, what is I squared equal to? Well, that's negative 1. And what is 2i cubed equal to? Well, I cubed is opposite I. So negative 2i cubed is going to be negative 2 times negative I. So you can see my work over here. I have 4 times I squared is negative 1 minus 2 times negative I. The negative 2 times negative I becomes a positive 2i, and I have a negative 4. Cool. Now let's look at number 2. I have negative I cubed. Now, let's think about this problem in this way. We know that a negative cubed is going to be negative. So, in my work over here, my first step is to say a negative quantity cubed is going to be negative, and I just cube the quantity to see what precisely I get. Well, I cubed is opposite I, so I get opposite of opposite I. That makes I. Okay, let's look at number 3. The square root of negative 2 to the 6th power. Now, if you're not careful and you just multiply the square root of negative 2 6 times over and put it all under one radical, you're going to make this error. First thing you need to do is represent the square root of negative 2 as I times the square root of 2. Then we can apply the 6th power to the I and to the square root of 2. Applying the 6th power to I to the 6th, well, that's I to the 4th times I squared. I to the 4th is 1. I squared is negative 1. Put it together, you have negative 1. Square root of 2 to the 6th power. Well, the square root of 2 squared is 2. If I'm putting the square root of 2 to the 6th power, that's me squaring it 3 times. It's like square root of 2 to the 2 to the 3. So if I were to put the square root of 2 to the power of 6, I would get 8. So I put it all together, negative 1 times 8 is negative 8. And that is my answer for number 3. Finally, for number 4, I have 1 over 2i cubed. Now, first thing I'm going to do is I'm going to apply this exponent to the 2 and to the I. So I have 8i cubed. Now, I cubed is negative I. So 8i cubed is negative 8 times I. This is not in a plus bi form, though. I would need to multiply by the conjugate. The conjugate of 0 minus 8i is 0 plus 8i. So I multiply numerator and denominator by 0 plus 8i. That leaves 8i in the numerator over negative 8 times 8 is negative 64. I times I is negative 1. Put it together and you have a positive 64. Reduce and you have 1/8 I. 0 plus 1/8 I is in a plus bi form, so that's acceptable. Now we're going to solve equations with complex solutions, and we have specific instructions for how to do problems 1 and 2. We solve each equation and express solutions in standard form. That's a plus or a minus bi form. So we look at this one and we're told to solve by taking roots. Okay? You can solve by taking roots if you have an x squared term, a constant, and no x. You can always solve by taking roots if your equation is in that form. So here's my work up here. I get my x squared on one side, my constant on the other. Then I square root both sides. But I need to remember, if I undo a squared variable with a square root, I need to include plus or minus on the other side. So positive or negative square root of negative 9 would be my answer. But we need to use imaginary numbers here. Plus or minus I times the square root of 9 tells me what I can do with that negative under the radical. Square root of 9, of course, is 3, and thus I have my answer. Plus or minus 3i. Okay, now let's look at one that's significantly more interesting. For problem number 2, we are told to solve using the quadratic formula, which means you gotta know the quadratic formula. I'll walk you through it. We have this to start with, but to use the quadratic formula, we need to get everything on one side and 0 on the other. Then a is 4, b is 16, and c is 21. Substituting in, we get opposite b plus or minus the square root of b squared minus 4ac all over 2 times a. You'll notice that after evaluating under the radical, I get a negative number, which is why number 2 is in this section. So now I need to render this in a plus bi form. That starts by acknowledging I. Square root of negative 80 is I times the square root of 80. Then I say 80 has a perfect square factor of 16. Square root of 16 is 4. And that's 4 times the square root of 5. 16 times 5 is 80. Square root of 16 is 4. Square root of 5 is, well, square root of 5. Can't do much with that. Now I can reduce. Negative 16 over 8 plus or minus 4i root 5 over 8 can be written as negative 16 over 8 is negative 2 plus or minus 4 over 8 is 1 over 2, so I have 1/2 I times the square root of 5. Root 5's in the numerator, so I can just keep root 5 in the numerator there. Root 5 over 2 times I. So I have a plus bi form. All right, you're all ready for your homework. Homework is due Wednesday. Enjoy. All right, welcome back, geometry. How we doing today? We're going to go to an interesting place in your notes packet. Go to Challenge for Algebra Skills, and that is after section 4.5. So look in your notes, section 4.5. After section 4.5, you will see some problems about piecewise defined functions, what I'll often call piecewise or just piece functions. Now, we're not going to do a lesson on how to graph piecewise functions because I have taught that for many years, and I know it's best if I am in person teaching that. So, I'm not going to do that to you. I'm not going to teach you digitally how to do piecewise functions. Yes, you're welcome. I heard those thank yous. Okay, so let's work with this function here. We're just going to evaluate with piecewise functions, okay? We're going to find f of opposite 3, f of 0, f of 2, and f of 3. First off, what precisely am I finding? Well, this is the function f of x. Depending on what the x value is, that's going to depend on what piece of the function I use. One of the pieces is x. One of the pieces is 2x minus 1. And one of the pieces is 7. So, let's look at f of negative 3. F of negative 3 says, if I substitute negative 3 in for x, what's the output? So I input negative 3. First question I should ask is, which piece am I using? I use the top piece if x is less than or equal to negative 1. Negative 3 is in fact less than or equal to negative 1. So I will use this rule. So f of negative 3 is negative 3. Look at that. And that is how I got my answer. Now let's look at f of 0. 0 is not in this first piece because 0 is not less than or equal to negative 1. Let's look at the second piece. Should 0 be here? Well, this is my piece of the function if x is between negative 1 and 2. 0 is between negative 1 and 2, so I'll use this piece. So f of 0 is equal to, plug 0 in, 2 times 0 is 0, minus 1 is negative 1. Now let's look at f of 2. This is the most interesting one by far. Let's see which rule I should use, which piece of the function is relevant for an x value of 2. Well, is 2 less than or equal to negative 1? No. Is 2 strictly between negative 1 and 2? No, because x has to be strictly less than 2, and last I checked, 2 is not less than 2. To use the third piece, x needs to be greater than 2. 2 is not greater than 2 either. So it looks like 2 has nowhere to go. That means that f of 2 does not exist. The function is literally not defined for an x value of 2. So we would simply say f of 2, that does not exist. Now let's look at f of 3. We know that 3 is not less than or equal to negative 1. 3 is not between negative 1 and 2, but 3 is greater than 2. So the rule that I use, the piece, is 7. Now, what does that mean? That means f of 3, put 3 in for x, equals, well, where do I put the 3 in this piece? There's nowhere to put it. So the answer is 7. F of 3 is, well, for all x values greater than 2, the answer is always 7. So that's why f of 3 equals 7. Now you're going to turn a little ways later in your notes. You're going to go to section 4.6, and then you're going to go to the end of that section after the homework, and there's more algebra skills. So just like the car outside my house where I'm recording, you're going to zoom right ahead in your notes. So, we're going to solve systems of equations by graphing, all right? For those of you who like to use many colors and highlighters, this section is a dream. For those of you who don't, that's okay. All right, so we're going to solve the systems below by graphing. For problem number 1, we have a 3-equation system. Now, there are many ways a 3-equation system could go, but you'll find this one's pretty tame. We're solving systems by graphing, so we need to graph this system of equations. We have these 3 equations right here, and I'm going to represent all of them in slope-intercept form. I'm going to solve each of the equations for y. Get y on one side, 0 on the other. Sorry, y on one side, everything else on the other. My apologies. And I'm going to argue that this problem number 1, 3-equation system, especially when we write it in slope-intercept form, is going to easily show one solution, and that's the point 2, 1. Now, how do I know that by graphing? Well, I need to graph these lines, which are conveniently in slope-intercept form. Here is the set of graphs. Y equals x minus 1 is the red. Y-intercept of 1, negative 1, y-intercept of negative 1, and slope of 1. Y equals negative x plus 3 is the line with the slope that's going down, and a y-intercept of 3. Y equals 1/2 x has a slope of 1/2. Run of 2, rise of 1. Run of 2, rise of 1. And a y-intercept of 0, since this is y equals 1/2 x plus 0. You'll see that all 3 of these lines meet up at the point 2, 1. What that means is that the point 2, 1, namely an x value of 2 and a y value of 1, form a true statement for all three of these equations. You can substitute 2 in for x and 1 in for y in each of these equations, and you get a true statement. That means that 2, 1 is a point on all three of these lines and is therefore a solution to this 3-equation system. Now let's look at problem number 2. Again, the first thing I'm going to do is take these equations and solve for y. Get y on one side and everything else on the other. So, let's look at how these would graph. They have the same slope, but they have different y-intercepts. Same slope, one to the right, 2 down, one to the right, 2 down, but different y-intercepts. This has a y-intercept of 1, and the bottom equation has a y-intercept of 3. So if they start, as it were, at different y-intercepts and have the same slope, they're never going to meet. Bummer. They have so much in common, but they'll never meet. I'm going to cry. Okay, so we would say there's no solution because these lines have no point of intersection. These lines up here have a nice convenient point of intersection, so they do have a solution. These lines do not. Let's look at number 3. These two lines are actually the same line, just written differently. If we were to solve for y, it's very easy to see. Here is that one line graphed. I graphed both of these lines, which are actually the same line. So how do I express the solution here? Well, if these two equations represent the same line, then that means that they have an infinite number of solutions, namely every point on this line that they share. So each point on the line y equals negative 2x plus 1 is a solution, okay? So if you get this sort of situation where you end up getting the same exact equation when solving for y and getting things in slope-intercept form, or via some other method, if you get the same equation twice over, you would express your answer as each point on the specific line is a solution. If you just say infinite solutions, my question is, which set of infinite solutions? The set that follows this rule. Those are the solutions you're looking for. All right, that will help you work on Algebra Skills Packet number 9 and number 10. Again, don't worry about the graphing of the piece functions in the beginning of number 9. Don't worry about that unless you want to try it. If you want to try it, go ahead. If you don't, we'll handle it when I am back in the classroom, Lord willing, quite soon. Have a great day. All right, calculus, welcome back. Pardon the low timbre of my voice. Everyone is getting sick in my family. I am not exempt. So, we're going to do this. Hopefully my voice doesn't put you to sleep. Wake up. Wake up, Leon. Anyway, so, implicit differentiation. Computing derivatives when the equation is not in terms of y. Stop dozing off, Gavin. Wake up. All right, so suppose f of x is equal to x times f of x cubed. That's our first problem. Find f prime of 1 if f of 1 is equal to 2. So here is how I would do problem number 1. This is just a restatement of the problem. First thing I'm going to do is find a derivative. The derivative of f is f prime. Then I would do product rule. 1d2 is going to be x times the derivative of f of x cubed, with f of x as a big variable, times the derivative of f of x. Then I would do 2d1, f of x cubed times x. Now I can find f prime of 1 by substituting 1. If I know that f of 1 equals 2, I can find f prime of 1 by substituting 1 for x and knowing that that evaluates to 2 in the original function. This is the line I would get if I made that substitution. Simplifying, I would get this line. Now I just need to solve for f prime of 1. F prime of 1 is like a big variable. So I can say, let's subtract 12 f prime of 1 on both sides. I get negative 11 f prime of 1 equals 8. Dividing, I would get negative 8 over 11. Now let's look at the second one. This first line is a restatement of the problem. First thing I would do again is find a derivative. We see we have a product rule situation, 1d2 plus 2d1. Here's 1d2, and then we have 2d1. All right, now let's look at a bit of simplification. Negative 2 times 2 is negative 4. And then you have x, g of x, g prime of x. And then we have negative 2 g of x squared. Cool. Now we're going to do our substitution. We're going to find g prime of 2 if g of 2 is equal to 1. We substitute 2 in for x everywhere, knowing that evaluates to negative 1 in the original function. Substituting 2, we would get this line. Then we simplify, and then again, we treat g prime of 2 like a variable. We add 8g prime of 2 to both sides, and divide, and there's our answer. Now we're going to do some higher order derivatives using implicit differentiation. Here's our interesting equation that features a product of x and y. You know it's going to be fun when there's a product of x and y. Stay awake, Danny. All right, so dy over dx is the first thing we're going to need to find. Here's my derivative. I see a 1d2, 2d1 product rule situation. 1d2 plus 2d1 gets us that far. Derivative of 3x, that is negative 3x, is going to be negative 3. Derivative of negative 4y is going to be negative 4 times the derivative of y with respect to x, dy over dx. Derivative of negative 11 is 0. Now, I get all of my dy over dx terms on one side via algebra, and all of my non-dy over dx terms on the other. I then factor out a dy over dx and divide out everything that's not a dy over dx to get my answer. There's my first derivative. Now, how, pray tell, do you find a second derivative? Well, in this case, we can take our first derivative and use quotient rule. Quotient rule says second derivative is low d high. The derivative of my upper part is going to be negative dy over dx minus high d low. Derivative of the lower is just 1 over the square of what's below. Now, if I want to do problem number 3, I'm going to need to substitute a value for x and a value for y. But I see this dy over dx here, and I don't know what to substitute in for that. Well, I know what dy over dx is. Dy over dx is this. So how about I just take this and substitute it for dy over dx? That means that my whole expression for the second derivative is in terms of x and y. So I put this in place of dy over dx, and there I have it. Mark, wake up. For dy over dx, second derivative, the derivative of dy over dx, evaluate it at 2 and 2.5. All you would do is you substitute 2 in for x, 2.5 in for y, and that is so much fun that I'm going to let you do that. Hope you had fun with that substitution. Now let's talk about inverse trigonometric functions. So just to review, a trig function maps an angle to a ratio of side lengths. In other words, take sine for example. Sine of an angle, we take an angle, is equal to the opposite side relative to that angle divided by the hypotenuse, ratio of side lengths. So an inverse trig function does the inverse. We're given a ratio of side lengths, and the function outputs the angle that would give us that ratio of side lengths. So if we were to talk about cosine of theta being adjacent over hypotenuse, so cosine of theta is adjacent over hypotenuse, then inverse cosine of adjacent over hypotenuse gives us theta, our input and output switch, as is what always happens when we find an inverse function. Now what's this arc cos thing here? Well, this is arc cosine. Arc cosine and inverse cosine are the same thing. They're not two different functions that just happen to do the same thing here. They're literally the same thing in two different notations. Now, I personally prefer this notation because it has the inverse symbol. This is not an exponent. It is a symbol that means inverse. However, a lot of folks like arc cosine, and that is okay as well. Now we're going to find the derivative of an inverse trig function. We're going to prove that the derivative of inverse sine is equal to this mess right here that interestingly does not feature a trig or inverse trig function at all. Pretty cool. So we're going to start with y equals inverse sine of x. Now, I don't really feel like dealing with inverse sine, especially because I'm trying to prove the derivative of inverse sine, and I don't know that. But I do know the derivative of sine. If I apply the sine function to both sides, I have sine of y equals sine composed of inverse sine of x. A function composed of its inverse just gets me x. So if I sine an inverse sine, that gets me x. So I have sine of y equals x. Now I'm going to do a bit of the kind of differentiation I've been doing in this section, implicit differentiation. The derivative of sine of y with respect to x is cosine of y times the derivative of y with respect to x. Derivative of x is just 1. Now, what I'm going to do is solve for dy over dx. I divide both sides by cosine of y, and I get dy over dx is equal to 1 over cosine of y. Now, that's a trig function, and I told you that we don't have any trig functions up here. Well, consider. If sine of y is equal to x, then that means, relative to this angle, sine of the angle y, because y has to be an angle if it's put into a sine function, sine of y is x over 1, opposite over hypotenuse. Now, even though it's not written in, this has to be a right triangle or else we could not use sine. So if sine of y is opposite over hypotenuse, x over 1, we can find the length of the other side using Pythagorean theorem. X squared plus what squared equals 1 squared. And the answer is this. Square root of quantity 1 minus x squared. So, if this is true when sine of y is x over 1, what then is cosine of y? Well, let's find out. Cosine of y is adjacent over hypotenuse. Square root of quantity 1 minus x squared over 1. So there you have it. Cosine of y is this, divided by 1, but it's this. So you have 1 over square root of quantity 1 minus x squared. derivative of an inverse trig function, no trig for to speak of. That's pretty cool. Now, I'm not going to prove all of these right here, but they all apply approximately the same logic. Okay? So we just proved the derivative of arcsine is that. The derivative of arccosine works about the same way. Derivative of arctangent is a little interesting and fun, but we end up getting the easiest formula of the three to memorize, and, pardon me, little cough there, and I made what some students consider the worst mnemonic device that has ever been forged by a teacher. So, take that for what it's worth, or don't take it at all. The choice is yours. So, we're going to compute the following derivatives. We're going to simplify wherever possible. So, the derivative of inverse cosine of 2x. Well, what's that going to be? Notice that the inner part is 2x. So when I do the derivative of the outside with the inside the same, I need to put a 2x in the variable spot, not just an x. So the derivative of inverse cosine of 2x is going to be derivative of inverse cosine, which is this, but I need to put the 2x in place of x, which I do. Then I do the derivative of the inside, which is 2. Multiplying and simplifying, I get negative 2 over square root of quantity 1 minus 4x squared. That is my answer. Now let's look at the second one. Pardon me. I appear to have forgotten derivative of arccosine in my answer, so I'll just tell you what it is. My apologies. I'll blame it on the sickness. So, the derivative of arctangent of x squared is going to be derivative of arctangent 1 over 1 plus x squared, except we need to put an x squared in the x spot, which I do, and then I multiply that by the derivative of the inside, which is 2x. Simplifying, I would get 2x over 1 plus x to the fourth. Now that derivative of inverse sine, it's just that. So you would just add this to the end to get the correct answer, unlike me. Now let's do this last one right here. This one has product rule, which makes it extra fun. So, the derivative of x times inverse sine of x is going to be 1 d2 plus 2 d1. Derivative of x is just 1. So there you have it. You can put the x up here in the numerator. That is a-okay. But you don't have to. This is fine and dandy. And now you have what you need to do the homework. Enjoy!